Your boss comes to you and says, hey, I'd like you to do some simulation. I'd like you to simulate a random variable that has an exponential distribution with, oh, let's say a mean of 2. And you're like, great, give me Mathematica. And your boss is like, sorry, we don't have the money for Mathematica. What can you do? Is it possible to still simulate an exponential distribution with a mean of 2? Simulate an exponential distribution with a mean equal to 2. Is that possible to do without something like Mathematica? Yeah, I mean, you can use R or Python, but you're like, I don't want to spend the time to learn R or Python. I only know spreadsheets and Mathematica, and we don't have Mathematica. So I've got to use a spreadsheet somehow. Is this possible with the spreadsheet? So you might go to the spreadsheet and you might know a little bit about equals RAND. We'll give you random numbers between 0 and 1 when you enter it. No input into the parentheses. You just type it in as is. If you copy and paste it, it gets updated. In fact, the previous thing you had gets updated. You're always getting numbers between 0 and 1. According to what distribution? What would make the most sense for RAND to be doing? What would be simplest? Uniform. A uniform distribution on the interval from 0 to 1 would be the simplest thing that the spreadsheet should be using. But that's not exponential. Is there a way to work with that somehow, though? Yes, there is. We do know that an exponential distribution has a PDF equal to 1 over beta e to the negative x over beta for x greater than 0, where beta does end up being the mean. Beta is mu is the mean of x. And we know that so that's the PDF. We know the CDF of such a distribution is going to be the integral of the PDF. Technically, since the random variable can only take on positive values, you could start that integral at 0. Okay, I'll go ahead and write it out. It's the integral from 0 to x of the PDF. I'll use my favorite Greek letter xi in here. Integrate f of xi to xi from 0 to x. Let's go ahead and do it. So integrating 1 over beta e to the negative xi over beta d xi. I love xi. Can you do that integral in your head? Can you find the antiderivative there? A little bit of thought reveals negative e to the negative xi over beta is an antiderivative, right? Double check that in your head. If you differentiate this, the chain rule will give you an extra factor of negative 1 over beta. Differentiate with respect to xi. Xi goes from 0 to x. Okay, now we need to go back to using x. So we get e to the negative x over beta minus negative e to the negative 0. E to the 0 is 1. Two negative signs make a plus sign. This becomes 1 minus e to the negative x over beta. So that is the CDF of an exponential distribution with mean beta. For our example, we want the mean to be 2, so beta would equal 2 for us. Once again, this is for x greater than 0. I wonder what would happen if I took my random variable x and plugged it into capital F. What? Can I do such a thing? And is it a good idea? Before we do so, what does the CDF of capital X look like? What does the graph look like? It's 0 over here. We're only concerned about when x is positive. The graph of the CDF, the graph of this function looks like this. And it's got a horizontal asymptote that's equal to 1. If I plug in a value of x, into this function that's positive, I'm going to get a number between 0 and 1 out. Just like a uniform distribution has values between 0 and 1. If I plug in observed values of this random variable into this function, would I get observed values of a uniform distribution between 0 and 1? That's definitely not obvious, but it's worth a try. Let's let capital U equal capital F of capital X. Now remember, random variables are technically not numbers. If you want to be extra technical about it, they're functions. I've mentioned that before, but to really understand what I'm talking about, it's like graduate level math. Don't worry about it. For us, they're just sort of ideas. Really, when I plug capital X into its own CDF, which is really what I'm doing here, capital F is the CDF of capital X. I'm going to put a subscript of capital X there. I get a new random variable, a transformed random variable. What is the distribution of this transformed random variable? I've mentioned the CDF method before. CDF method before. Let's use it again. What is the CDF of this new random variable U? I'll call it capital F sub U. These are different functions here. The subscript is important. If I can figure out the CDF of capital U, then I can figure out the distribution of capital U. If you know the CDF, you know the distribution. You can figure out the PDF, figure out the mean. What should I call the variable for capital U? Well, how about little u? I'll make it kind of cursive there. As always, I've said this, 5, 6, 7, 8 times. The CDF of any random variable, discrete or continuous, is the probability that that random variable is less than or equal to the given number. Always, always, always. Okay, what should I do with this? Well, use the fact that capital U is a transformed version of capital X. Okay, great. Maybe I should use the formula for capital F sub capital X. I didn't put a subscript up here, but now I'm doing so. This formula. Again, for us, beta is going to be 2, but let me leave it in there as an arbitrary beta. Replace the little x there with capital X. Again, you kind of might shake your head and wonder, can this really be done? The answer is yes, these formal manipulations do work. What should I do with this? Maybe simplify this somehow. Maybe I should solve for capital X. Solve this inequality. Maybe it's worth a try. See what happens when I do that. How? Well, I guess subtract 1 from both sides first. Then multiply both sides by -1. However, if you do so, I don't know if you remember this from what, 8th grade? When you multiply both sides of an inequality by a negative number, the inequality changes direction. I guess I got to take the log of both sides now. Oops, I've been making mistakes here. This capital X, sorry. Take the log of both sides to get rid of that e. And technically, we should use the fact in writing that step that the natural log function is an increasing function. Ln of x is increasing, is technically important, so that the inequality stays the same direction when I take the log of both sides. If one thing is bigger than another and you plug those things into an increasing function, the results have the same inequality relationship. The function's graph is going up. A is less than B. You plug A and B into the function. F of A will be less than F of B. The inequality stays the same direction. If the function had been decreasing, you'd have to flip the inequality. We're almost done. Multiply both sides by negative beta, I guess. Once again, the inequality is going to change directions. Interesting. Okay. Can I work with this? Yes, you can, because this is related to capital F sub X again. How? It's the probability that capital X is less than or equal to something. That's a value of the CDF for capital X. Oh, are all these steps really needed? Yeah, technically they are. Although you actually can do this more abstractly and it's a little quicker than what I'm showing you here. But I think it's good to see this. You understand? We'll go over each step. I hope you've understood each step at least so far. I guess now I got to plug that into the formula for capital F. Got to use this formula again. 1 minus e to the negative, replace x with this entire thing. Negative beta natural log of 1 minus u. The two negative signs cancel. The betas will cancel. I'll get 1 minus e to the negative natural log, or the negative signs cancel, excuse me, plus natural log of 1 minus u. Hey, this is looking nice. E and the natural log cancel. They're inverse functions. This becomes 1 minus u. U. Really? Is it that simple in the end? Yes, it is. This is right. I didn't make a mistake. Let's double check everything and make sure we understand each step. What was my goal? My goal was to try to find the CDF cumulative distribution function of this transformed version of X, where I plugged the random variable X, an exponential distribution with mean beta, into its own CDF. Find the CDF view by definition. That's a definition of CDF. You get this? This next step is by definition of U. This formula here. This next step is the formula for capital F sub X. This next step is algebra. Next step is algebra. Next step is algebra and the fact that ln of x is increasing. Next step is algebra. And this is the definition of a CDF again. And here is using the formula for capital F of x again. Capital F sub x. And then algebra or simplification. Algebra / simplification is what's left over here. And we get something very simple in the end. The CDF for capital U is a linear function of U with a slope of 1 going through the origin. Its graph looks like this, straight line, slope of 1. I guess only when U is between 0 and 1, though. Technically, as always, it would be 1 over here and 0 over here. And why did I call it U? Because it's got a uniform distribution. Its derivative is always 1. This is capital F sub U of U. Its derivative is its PDF. It equals 1 if U is between 0 and 1. The PDF looks like this. 0 otherwise. That's little f sub u of little u. Uniform distribution, how about that? Okay, wait a minute. What were we trying to do? We were trying to simulate an exponential distribution with a mean of 2. Does this hint at how to do so? Sort of, maybe not completely. If this gives you a uniform distribution, I guess that means to get the original variable, you need the inverse function, which does exist when x is positive in this example. This function right there is not 1-to-1 over the entire number line because it is not fails the horizontal line test over here. But if you ignore that part right there passes the horizontal line test. It's a 1-to-1 function. It's got an inverse function. And in fact, the inverse function is essentially that. Right? I essentially, well, so we're solving an inequality here for x, but if that were an equality instead of an inequality, I get x equals this. That's essentially the inverse function right there. And if beta is 2, let's give it a name. If beta is 2, f sub capital X inverse of u then would be negative 2 ln of 1 minus u. So what am I trying to get at here? If we can simulate values of u with equals RAND in the spreadsheet, we can plug those numbers into this function and get simulated values of x, maybe. Should we try it? Negative 2 ln of 1 minus u, go back to the spreadsheet. Negative 2 ln, yeah, and on mathematical natural logs log, but in a spreadsheet it's ln. 1 minus u. And actually, if u is uniform on the interval from 0 to 1, we probably wouldn't really have to do 1 minus u. It probably would be fine to do u and get a similar. It's not the inverse function anymore, but it would give us the same kind of outputs. Probably exponential still. So the numbers in the first column are uniformly distributed on the interval from 0 to 1. Let's get a bunch of them. Well, maybe 40 of them. And the numbers in the second column are taking those numbers and plugging them into that inverse function, negative 2 ln of 1 minus u, to get ideally simulated values of an exponential distribution with mean 2. Now you can see some of these numbers are indeed bigger than 1. Some are fairly large, like that 8.27 is fairly large. Is there a way to check if this seems to be simulating an exponential distribution with mean 2? Well, we could at least find the mean, B1 through B40. Of course, when I do this, it's going to change all the numbers again, but that's not a big deal. Equals average will compute a mean. With this particular data set, I don't know if you can see this numbers, it says 1.78. Let's enter it. We'll get new numbers and a new mean. Happens to be 1.77. If I re-enter the number, I get something close to 2. Re-enter it again, I get something a little bit bigger than 2. Yeah, I could keep redoing the simulation over and over again. And I always get a mean that's somewhat close to 2, sometimes smaller, sometimes bigger. That's making it seem reasonable that it really is simulating at least a distribution with a mean of 2. Is it really an exponential distribution? Can we graph these? How would we graph them? Insert chart. What kind of chart? Histogram? That looks kind of like an exponential curve going down, doesn't it? What is this histogram doing? It's counting how many numbers are in each range here, from 0 to 1.92, then 1.92 to 3.83, 3.83 to 5.75. For example, looks like there's 4 numbers in that range. the spreadsheet's deciding where to cut these numbers off. It made an executive decision for me. Not necessarily the best choice, but I do see something that's got a pattern going downward, kind of like an exponential decay. Yeah. This does work. This is what you would want to do to simulate such a distribution if all you have is a spreadsheet. Think it's fun? You're smiling, Abby. Is that because it really is fun? Okay. Simulation is really important on the job. And sometimes you can do things theoretically and you don't need to simulate. But other times, you don't know how to do things theoretically, and so you have to simulate. An example that comes to my mind is I watched a video once. They were talking about probability in real life applications, and they were interviewing a traffic engineer. And the traffic engineer, what were they doing? They were trying to set up models of street lights in like New York City or something. You know, you got all these roads going all over the place, all these intersections, some at strange angles. And you got to, you know, decide what the traffic light pattern should be to make traffic flow as smoothly as possible. Now taking into account walkers and bikers and stuff too, and taxis, and you know, it's crazy in New York City, and that's why it doesn't work so well. But you know, if you don't design the traffic lights, their timing well, then that would be bad. Now, of course, there's also sensors keeping track of what the traffic's like and that kind of thing. So there's a feedback, but trying to model such a thing with theoretical probability, yeah, you probably can do it to some extent, but in the end, you probably have to use simulation. You have to construct a model of the city streets in your computer and assume various things about the traffic and then tweak the traffic light timings to try to make things flow smoothly. Okay, so it is related to real life.